Dear friends, welcome to my video on deep neural networks for acoustic modeling in speech recognition. Kindly click on the CC button for subtitles. First off, acoustic modeling is basically a fancy term for how computers understand and process the sounds we make when we speak. In the context of speech recognition, it's about how a system can hear you say, "Hey, what's the weather like today?" and actually understand what you mean. Now, traditional speech recognition systems used simpler models, but they had their limits. Then along came DNNs, and they shook things up in a big way. DNNs are a type of artificial intelligence. Imagine them like really smart brains made of layers and layers of neurons, only these are artificial. So, why are DNNs such a big deal for speech recognition? Well, they're incredibly good at dealing with complex patterns, and human speech is nothing if not complex. With DNNs, systems can handle variations in speed, accent, pronunciation, and even background noise much better than before. The way it works is pretty interesting. When you speak, your voice gets converted into a digital signal. This signal then goes through the DNN, which has been trained on tons of speech samples. As it passes through the layers of the network, the DNN extracts features, recognizes patterns, and essentially learns to understand what you're saying. One of the coolest parts is how DNNs are trained. They use something called deep learning, where they're fed a massive amount of speech data. This can include different languages, dialects, and even noisy environments. The network learns from all this data, getting better and better at recognizing speech patterns. But it's not all smooth sailing. DNNs need a lot of computational power, and they can be a bit of a beast when it comes to training them. Plus, they need a lot of data to learn effectively, which isn't always easy to come by. Despite these challenges, DNNs have revolutionized speech recognition. Today, they're a key part of voice assistants like Siri, Alexa, and Google Assistant. Thanks to DNNs, these systems can understand us better than ever, making our interactions with technology more natural and intuitive. Modern DNN approaches versus hybrid acoustic models. The success of modern DNNs over previous models is attributed to a larger number of network parameters, more hidden layers, and the use of context-dependent triphones instead of monophones. Initially, unsupervised pre-training for initializing DNN weights was deemed important, but later, purely supervised training from random initial weights was found to yield almost identical performance. Label set and forced alignment in training data. The training data, originally containing word-level transcriptions, is processed to assign synonym labels to each frame. This is achieved through forced alignment, aligning ground truth transcriptions with synonym labels. The baseline HIM-GMM system is used for this purpose, emphasizing the importance of context-dependent states for modern large vocabulary continuous speech recognition (LVCSR) systems. Neural network architecture. The architecture of neural networks used in acoustic modeling has evolved significantly. Modern DNNs, characterized by multiple hidden layers, depth, have shown improved performance over single-layer networks. The exact depth needed for optimal performance is not fully understood. Alternatives like deep convolutional neural networks, DCNNs, and deep recurrent neural networks, DRNNs, have been explored, each offering unique advantages in processing the temporal dynamics of speech signals. Loss function for training DNNs. The cross-entropy loss function is the standard for DNN acoustic models, focusing on maximizing the likelihood of observed labels. However, to better integrate DNNs into the overall automatic speech recognition (ARSA) system, discriminative loss functions have been introduced. These begin with standard cross-entropy training and then either add or switch to a discriminative function for more refined training. Optimization algorithm. The optimization of DNNs involves dealing with non-convex problems. Stochastic gradient descent, SGD, is the most common method, with various alternatives being explored for improved results. Advanced methods like quasi-Newton algorithms and ADA-GRAD have shown promise in optimizing DNNs more effectively than traditional SGD methods. Thank you for watching my video. Kindly subscribe to my YouTube channel and give a thumbs up. Thanks for your support.